So today we're going to be solving a first order RC network. We want to find the voltage across the capacitor for when T is greater than 0, and we want to plot the response. So the basic function of this network is when T equals 0, the switch opens up. So first off, how we solve it is when T is less than 0, so before when the switch opens up, the capacitor is in a steady state. So we want to solve for the steady state network first. So in order to do that, we make sure that the voltage across the capacitor is an open circuit. So if we redraw the circuit, we have the 9-volt current source, or voltage source. We have the 6K resistors. Alright, so now the switch is still closed, so we just draw the line, and then we draw the open circuit, which is across the capacitor. We have the 6K resistor, and then we have the 2 milliamp current source. Okay, so let's label nodes. So first, we'll start with the ground. Say this node is 9 volts. Say this node is VA. This node is VA because they're connected. All the way along is VA. So that means that this open circuit is just, the voltage across the open circuit is just VA. So now let's label the current. So let's say the current is going this way and this way across the 6K resistors on the left side, and down the 6K resistor on the right side. Okay, so now what we do is we apply KCL. So the current going into the node equals the current going out of the node. So the current going into the node, we have two currents. We have this current and this current over here. So we say 9 minus VA divided by 6,000 plus 2 milliamps is equal to the current going out. So we have two currents going, this current and this current, which is VA minus 0, since it's grounded, divided by 6,000, plus VA minus 0, because it's grounded too, divided by 6,000. Okay, so now what we could do is we could solve for VA. So we have 9 divided by 6,000 plus 2 times 10 to the negative 30 is equal to VA multiplied by 1 divided by 6,000 plus 1 divided by 6,000. We moved this all the way to the right side, so this is 1 divided by 6,000 too. And yeah, from there we could solve for VA. So this side equates to 3.5 times 10 to the negative 3 is equal to VA times 5 times 10 to the negative 4. And if we divide this by 5 times 10 to the negative 4, we end up with VA equals 7 volts. So this means that before when the switch opens up, the open circuit voltage across the capacitor, since it's in steady state, is equal to 7 volts. Okay, so we know the voltage across the capacitor before the switch opens up. So let's find the voltage across the capacitor when the switch opens up. So let's figure that out. In order to do that, let's redraw the circuit. So when we redraw the circuit, we want to show that the switch opens up. So what we do is we just do the voltage source, which is 9 volts. We have the 6K resistors. Now the switch is open, so we could just say that, or it looks like this. It's almost like it's pretty much an open circuit at this point. And since the capacitor is not at steady state anymore, we put in the capacitor, which is 2.5 microfarads. We end up with the 6K resistor, and we have the 2 milliamp current source. Okay, so in order to solve for this circuit here, we know that the voltage across the capacitor, V0, depends on the time, so V0 t. Well, this side of the left side of the circuit, we could say that pretty much the current goes into this resistor, goes into this resistor too, and it just cycles through. So we could kind of split this and leave this side on its own, since this current is not affecting the components on the right side of the circuit. So we could redraw the circuit. Let's do that. So we have the capacitor here, which is 2.5 microfarads. We have 6K resistor, and we have the current source, which is 2 milliamps. Okay, so the voltage across the capacitor depends on time. So what we could do is we could apply nodal analysis, and we could solve for V0 t. So the current across the capacitor, you could say it's going that way, current across the resistor is going that way, and we could apply KCL, the nodal analysis. So the current going in, which is 2 milliamps, 2 times 10 to the negative 3, is equal to the current going out. Well, the current going out of the resistor is just V0 t minus 0, since the bottom is grounded, divided by 6,000, plus, now the current going through the capacitor is just equal to C times d V0 t dt. So let's put in the capacitance and try to make this a little more neater. So if we put in the capacitance, and with 2.5 times 10 to the negative 6 d V0 t divided by dt plus V0 t divided by 6,000 equals 2 times 10 to the negative 3. So to make this even more cleaner, what we could do is we could say put these in a simpler type of format. So d V0 t dt is just V0 t with a dot on it, just to indicate that it is the first order derivative. So 2.5 times 10 to the negative 6 V0 with a dot to indicate that it's a derivative, first order, plus V0 t by 6,000 equals 2 times 10 to the negative 3. Okay, so this is the first order circuit describing when the switch opens up. Now what we want to do is we want to try to find V0 t. In order to do that, we apply this type of algorithm in order to solve for the linear differential equation. So first off, we want to isolate or remove this 2.5 and just have V0 t, V0.t, sorry, on its own. So we divide everything by 2.5 times 10 to the negative 6. We're going to do V0 t plus 6,000 times 2.5 times 10 to the negative 6. That just equals to 1 divided by 0.015 V0 t equals to 2 times 10 to the negative 3 divided by 2.5 times 10 to the negative 6. That equals 800. So now we just have the coefficient in front of V0 dot t is equal to 1. That's all we did, just to make it a little more cleaner. And now we could apply the algorithm. So the algorithm states that this coefficient right here is equal to u to e to the power of the integral of this coefficient, 1 divided by 0.015 dt. In order to find this integral, it's just equal to e to the power of t divided by 0.015. Okay, so that's pretty much finding the integrating factor, u of t. And we want to multiply everything in the differential equation by u of t. And we integrate both sides in order to deal with the constant of the integration, and then we will be able to solve for v naught t. So let's do that. So if we multiply everything by the integration factor, we end up with u times v naught t is equal to u times this coefficient, which is 2 times 10 to, oh sorry, this coefficient right here, because we simplified it, is 800. And what we do is we integrate both sides. So once we integrate both sides with respect to t, we end up with u of t, which is e t 0.015 v naught t dt is equal to e t divided by 0.015 times 800 dt. So we integrate both sides, we end up with e t divided by 0.015 v naught t is equal to, now the integral of this is just 1 divided by 0.015, so we have e to the t 0.015 divided by 1 divided by 0.015 times 800 plus c. C is just the constant. Okay, so let's just simplify. So we have e to the power of t divided by 0.015 v naught t. Now 800 times 0.015, that equals to, let's see, that equals to 800 minus 0.05, that equals 12. So we end up with 12 e t divided by 0.015 plus c, which is the constant. Now in order to isolate for v naught t, we divide everything by by this. So once we divide everything by that, we end up with v naught t is equal to 12. These are, since this is divided by itself, this becomes 1 plus c times e, since it's 1 divided by this becomes negative, so e to the negative t divided by 0.015. Alright, so this is pretty much the equation of v naught t when the switch opens. So what we need to do is we need to find what the constant is. In order to find what the constant is, we know that when v naught is 0, it equals to 7, which is the steady state in which we calculated before. So for this one, so basically when v naught equals 0, when v naught is equal to 7, that's when t is equal to 0. So when the switch is just opening up. So we say v naught at 0 is 7, and that equals to 12 plus c e to the power of 0, right, divided by 0.015 since t is 0. So this ends up being 7 equals 12 plus e to the power of 0, that's 1, so that's just c. So c ends up being negative 5. So if we plug in the constant into the equation, we end up with v naught t is equal to 12 minus 5e to the negative t divided by 0.015. And this is the equation of the capacitor when the switch opens up. Okay, so now what we want to do is we want to plot the response just to see how it is. So when we plot the response, just put the equation in again. So V naught t is equal to 12 minus 5e negative t divided by 0.015. Once we plot the equation, we have V naught t. When t is 0, just before when the switch opens up, it's at 7 volts, right? So in order to get this part of the equation, we know that it's at steady state, so in which we calculated from before. So in order to show that into the equation, what we could do is we could say, okay, well, V naught at 0 is just 12 minus 5e to the negative 0 divided by 0.015. This becomes 12 minus 5. This becomes 7, just 7, all the way across steady state. And when t is greater than 0, it actually reaches steady state again at 12 volts, which looks something like this. It keeps going all the way to infinity at 12 volts. In order to find that, we say, okay, well, V naught at infinity is just 12 minus 5e to the negative infinity divided by 0.015. Now, e to the negative infinity, that just equals pretty much to a large value. So e to the negative infinity, we'll just put in a large number that actually equals to 0. So we have 12 minus 0 equals 12. So we could see that beforehand, before when the switch opens up, the capacitor is at steady state at 7 volts. And when the switch opens up, the capacitor ends up at another steady state at 12 volts. So it charges up to a higher voltage value. In order to find when the voltage reaches its steady state at 12 volts, we could say that pretty much that T equals 5 tau. That's just a rule of thumb indicating that when the time is 5 times tau, that it reaches 12 volts. So 5 times tau is just equal to 5 times tau, which is the bottom of the exponent of the exponential function. So it's 5 times 0.015, and that's just equal to 5 times 0.015. That's 0.075 seconds. So pretty much at 0.075 seconds is when the capacitor reaches a steady state of 12 volts when the switch opens up. Alright, this is solving pretty much the first order RC transient network. And yeah, I hope you enjoyed the video. Thank you.